So far this series has built up algebraic structures. Monoids in the peasant post, rings in the modular post, Euclidean domains for polynomials, product monoids for accumulators. But structures alone are only half the story. The other half is the maps between them, the functions that carry one structure into another while keeping its shape intact.
Okay, but what actually connects one structure to another?
A homomorphism is a function f from A to B between two structures of the same kind that preserves the operation. In symbols, take the symbol A and combine it with B. Then apply f. That must equal combining f of A with f of B. The operation on the left lives in A, the operation on the right lives in B. The function f commutes with the operation. That is the entire definition. Read it as two paths that have to agree. You can combine A and B first, inside A, and then apply f. Or you can apply f to each of them first, landing in B, and then combine the results there.
So it does not matter which path we take.
Not a bit. A homomorphism is exactly the promise that both paths reach the same place. Structure goes in, and structure comes out. Here is the shape we are going to hold fixed. Take the symbol A and combine it with B. Then apply f. That must equal combining f of A with f of B. We will keep this shape pinned at the top and change only two things underneath it: the structures on each side and the function between them. Every example in this post is the very same equation wearing different clothes. Take strings under concatenation with the empty string as identity. Map them to the integers under addition. The map is length. The length of a concatenation is the sum of the lengths. Length of hello joined with world is 10, which is 5 plus 5.
Wait, is that just a coincidence?
It is not a coincidence. It is the homomorphism property. Now fix the source as lists of integers under concatenation, and watch one source feed two different targets. Send a list to the integers under addition with sum. Sum of 1, 2, 3, joined with 4, 5 is 15, which is 6 plus 9. Send the same lists to the integers under multiplication with product. Product of 2, 3, joined with 4, 5 is 120, which is 6 times 20. Same source, different target, same shape. Here is a familiar one in disguise. The positive reals under multiplication form a monoid. The reals under addition form a monoid. The logarithm maps one to the other. Take the symbol A and multiply it by B. The log of that product equals the log of A plus the log of B. Log of 2 times 3 equals log of 6.
Is that why slide rules could turn multiplication into addition?
Exactly that. That defining property of the logarithm is just the homomorphism law. None of these are arbitrary functions we picked out by hand. Length, sum, product, logarithm, each one is a structure-preserving map. The same equation holds every single time, because each map respects the operation underneath it. Now the deepest example. Lists are what algebraists call the free monoid. The most general monoid you can build on a set of generators.
What makes a monoid free exactly?
Given any set T, the finite lists over T, under concatenation, form a monoid. Free means it imposes no relations of its own beyond what every monoid must obey. It just remembers the elements in order. Freeness comes with a universal property. For any monoid M, and any function f from the generators T into M, there is exactly one homomorphism from the free monoid on T to M that extends f. Not 0 and not many, exactly one. And that unique homomorphism has a name you already know. It is fold. Here is fold written as algebra. Start the result at the identity of the target monoid. Walk the list, and for each element x, combine the running result with f of x using the monoid operation. So folding f over the list A, B, C works out left to right. First combine f of A with f of B. Then combine that result with f of C. The function f maps each generator into the target. Fold extends that map to whole lists. Every example from before is now just a choice of f. Sum is fold, where f sends each integer to itself in the additive monoid. Product is fold, where f sends each integer to itself in the multiplicative monoid. String concatenation is fold, where f is the identity on strings. One algorithm, and the target monoid decides what it computes. So here is the punchline. Every time you write a loop that accumulates a result by combining elements one at a time, you are computing a fold. And every fold is a homomorphism from the free monoid into wherever you are accumulating.
Wait, so I've been writing homomorphisms this whole time.
The loop you write by habit is a structure-preserving map you did not know you were writing. Remember the very first episode. We computed x to the n by repeated squaring. Now look at the exponent as data. The binary representation of n is a sequence of bits, and a sequence of bits is a word in the free monoid. On the two symbols 0 and 1. For example, 13 in binary is 1, 1, 0, 1.
Wait, so the exponent itself is a word in a free monoid.
Exactly that. The power function reads that word one bit at a time. On a 0, it squares the running result. On a 1, it squares and then multiplies by x. So each bit maps to an operation. A 0 becomes square, a 1 becomes square and multiply. Those operations live in the endomorphism monoid. The functions from the monoid to itself, composed one after another. And power folds that sequence of operations into a single result. The binary representation decomposes the exponent into bits. The homomorphism reassembles it in the target monoid, giving x to the 13. The correctness of repeated squaring is not a clever trick. It is a consequence of this algebraic structure, a fold of bit operations from the free monoid on 0 and 1.
So what does being a homomorphism actually buy us?
Suppose f is a homomorphism, and you can split the input into parts. Take 3 pieces, the symbol A, B, and C. Combine them first, and then apply f. And that equals applying f to each one separately, and combining the results. You can compute f on each part independently, and then combine the answers. That is the algebraic reason parallelism works. Associativity alone lets you reparenthesize to regroup the combining however you like. The homomorphism property is what lets you distribute the function across the parts in the first place. Split the data across threads, compute on each piece, merge the results. This is exactly the shape of map and reduce.
Does every function pass that test?
Not even close. Take the square function on the integers under addition. Is it a homomorphism? Check it. 2 plus 3 all squared is 25. But 2 squared plus 3 squared is 4 plus 9, which is 13. 25 is not 13. Square fails the law. So square cannot be parallelized by splitting and combining. And that is the real gift. The algebra itself tells you in advance which functions admit this decomposition and which do not. You do not have to guess whether a computation parallelizes. You check whether it is a homomorphism. Step back and look at every homomorphism in this episode. They all have the same shape. 1, 2 monoids, a source and a target. 2, a function between them. 3, the function commutes with the operation. Length, sum, product, logarithm, fold, even the Peasant algorithm. Every one of them fits this template.
All of that from just one condition holding.
When that third condition holds, 3 things come for free. Composability. Homomorphisms compose, so you can chain structure preserving maps and stay structure preserving. Parallelism. Split, compute, combine, and correctness. The algebra guarantees the answer, so you do not have to rederive it for each new type.
So what is the one-sentence version of all this?
Structures are the nouns of this series. Homomorphisms are the verbs. the maps that carry structure from one domain to another. Fold is the universal one, the single map from the free monoid that every accumulation secretly is. Algorithms arise from algebraic structure, and homomorphisms are how that structure travels.